Hello. Before we even start balancing the redox equations, first we need to learn how to assign the oxidation states to atoms in a molecule. So let's start with the water. We'll be using our oxidation table when we can find the most common oxidation state of the most common atoms in molecules. So for example, we have oxygen, and the most common oxidation state for oxygen is -2. So we just put a -2, and for hydrogen is +1. We have to notice as well that the overall charge of the molecule must be equal to 0. So if you sum all the oxidation states or individual atoms in molecules and you add them together, it must be equal to 0. So let's do it for the water molecule. You see, we take that index 2 here, which is besides the hydrogen. So 2 multiplied by +1, that's the oxidation state of the hydrogen in molecule, and we have 2 atoms in the molecule, so we're multiplying that by 2, adding the multiplication of oxidation state of the oxygen in the molecule, and we have only one atom of oxygen, so that's why we have him, and why we have here 1, and all of that must be equal to 0. That's the charge of the molecule as a whole. So let's do calculation. Is it right or not? It's 2 minus 2 equals 0. That's true. So our oxidation states assigned to individual atoms in the molecule of water are correct. Let's do it again for sodium oxide. So as we see, the oxygen has an oxidation state -2 from the table, and for the sodium it belongs to the group first group of the in the periodic table, so it's +1. And now check the overall charge of the molecule. So 2 atoms of sodium, so 2 multiplied by +1 plus 1 multiplied by -2 equal 0. Again, oxidation states of the atom in the molecule are correct. The overall charge is 0. Another example is a chlorine dioxide. We can find the oxygen in our table. It's a -2 for oxygen, but we cannot find the chlorine. We have a fluorine here, but we don't have a chlorine actually here in the table, so we need to calculate it. So we just put the X as the oxidation states of chlorine in the molecule of chlorine dioxide. So how to do it? We have one atom of chlorine in the molecule, so as we did earlier, just one. We multiply it by the oxidation state of that atom, which is X, and add the sum of oxidation states of all atoms of oxygen which are present in that molecule, so it's 2 multiplied by -2. The overall charge of the molecule must be equal to 0, so it's equal to 0. And to the calculation is X minus 4 equals 0, X equal 4. When we're moving the value from one side to the other side, we're changing the sign, so -4 becoming +4, and that's the answer. And if we check it, so we have one chlorine atom in that molecule, so 1 multiplied by +4 +2, because we have 2 atoms of oxygen, multiplied by -2 and overall charge of the molecule 0. So we have a 4 minus 4 equal 0, which says that is correct. Let's move forward. Now we calculate oxidation states or individual atoms in the sulfuric acid. So from the table we have that oxygen as a -2, hydrogen as a +1, and sulfur unknown. So following again our pattern, so 2, because we have 2 atoms of hydrogen in one molecule, multiplied by the oxidation state of the hydrogen, plus 1 multiplied by X, because we have one atom of sulfur in our formula, and X is the oxidation state, which is unknown for us, plus 4 multiplied by -2, because we have 4 atoms of oxygen in that molecule, and -2 is the oxidation state of each one. And that's everything must be equal 0, which represent the overall charge of that molecule. So it's 2 plus X minus 8 equals 0, which gives us X minus 6 equals 0. So X is equal 6. Because -6, we move into the other side and we're changing the sign. So that's the answer. Let's do one more example. Calculate the oxidation states of individual atoms in nitric acid. So for oxygen, we will find in our table -2, for hydrogen +1, and for nitrogen X, which represent unknown. So 1 multiplied by +1, which is 1 is the number of atoms of hydrogen, +1 represents the oxidation state of the hydrogen, plus 1 multiplied by X, plus 3 multiplied by -2, and overall charge of the molecule is 0. So it's 1 plus X minus 6, so X minus 5 equals 0, X equals 5. -5, move to the other side, so don't forget to change the sign. So oxidation states of individual atoms in the molecule of nitric acid is, that's the answer. Before we balance that equation, we need to look here. We have a rules which we follow when we want to actually balance that equation. So we have 5 steps, and first step is assign oxidation state to all atoms in the molecule. That's what actually we learn to do for the simple molecules. And at the beginning we will be dealing only with a simple example, because more advanced require a little bit more knowledge, and the table actually need to be replaced by periodic table and other things, knowledge of electronegativity and things like that, to actually find out the oxidation states, but never mind now. So we'll be dealing only with the simple examples. So first thing, just what we learn is assign the oxidation states to all atoms in the molecule. We didn't use all the values we had in the table. For example, we have information here that the oxidation states of any uncombined element is 0. Uncombined element is the element which actually exists by itself, like here carbon. we have it's uncombined, it's only carbon. And here we have an example of our uncombined elements like the oxygen, chlorine, hydrogen, sodium. So the uncombined element, the oxidation state of an uncombined element is 0. So we can assign the 0 to the carbon. It's from the definition. So nothing to do with that at this moment. We as well learn how to calculate the oxidation states in the more complex molecule, like the sulfuric acid, for example. I just do it quickly here. So we know that the hydrogen is +1, oxygen is -2, 4 by -2 is -8, +2 is -6, so balance -6, we need the +6. For the carbon dioxide, oxygen is -2, -2 by 2 is -4, to balance -4 to get a 0, we need the +4 on the carbon. Sulfur dioxide as well, -2, to actually cover that -4 charge from the oxygen. We need the +4 on sulfur, and on our water, -2 + 1. So when we finish the first step, assign oxidation state to all atoms, what actually we did. The second step is find out which elements change oxidation state. So we see that the carbon is changing oxidation state, and as well sulfur is changing oxidation state. So we have a 1 and 2. When we have all elements which changing oxidation state, we're moving to step 3. Balance the number of electrons lost and gained in partial equation. It may actually sound complex, but it's very, very easy. So we do the partial equations for those elements. So we have a carbon with the oxidation state 0, and it's actually changing to the carbon with oxidation state +4. Here is +4. And another element with changing oxidation state is a sulfur, and sulfur from the oxidation state +6, changing the state to sulfur +4. And now we see that balance the number of electrons lost and gained. So which one lost and which one gained electrons? Electrons has a negative charge, so actually to move from the state 0 to +4, the atom need to lose electrons, so -4 electrons. And to move from the oxidation state +6 to +4, we need to gain electrons at only 2. And now that what we have here, it's called partial equation. But they are not balanced, and we need to balance the number of electrons. The principle is very easy. The number of lost and gained electrons must be equal. So we see that the lost electrons by carbons are 4, and the gain by sulfur are only 2. So how to balance it? We need to find the simple ratio between them. So in this particular example, actually we'll see if we multiply that second partial equation by 2, it will be then balanced with the first one. So if we multiply the second equation by 2, we'll get the 2 atoms of sulfur on oxidation state +6 plus 4 electrons, and 2 atoms of sulfur which oxidation state +4. And we see we only multiply the second one, and now the second one gaining the amount of electron which are lost in the first one. So we may say that the equation are balanced. I just rewrite the first one. So here. And we may see now that the partial equations are balanced, as sulfur is gaining 4 electrons and carbon is losing 4 electrons. So what to do next? That number 2, which actually appear here now after balancing partial equation, must appear as well here. As here we have a sulfur on the on the oxidation state of 6, and here is the sulfur with oxidation state 6. So that 2 is moving here, and that 2 need to as well appear before the on the right side before the sulfur on oxidation state 4. So here. And before carbon we have a 1. We're actually not writing the 1, so here is the 1. And here is the 1. So now we actually are calculating by inspection the atoms in the molecules. We have a 1 carbon here, 1 carbon here, it's correct. We have a 2 atoms of sulfur on that side and 2 atoms of sulfur of this side. That's as well correct. Now we calculating the oxygen and hydrogen as the last one. So oxygen, we have 8 oxygen atoms on the left side. On this side we have a 2 plus 4 is 6, 7. So 1 is missing on that side. So we need to add it. So just to give an extra, we cannot just change the number here, and we cannot change the number here, because those numbers here are actually reflecting our partial equations, so cannot be changed. The only place we can we can change the number is here. So we add a 2 here, and calculating oxygens again. On the right side and on the left side 8, and hydrogen, here we have 4 hydrogens, and here as well 4 hydrogens, and everything is balanced. So again, in this example we follow the rules. Assign oxidation states to all atoms. So here is -2 for oxygen from our table. Potassium in its first group, which is +1, and after calculation for nitrogen we have a +5. Carbon oxidation state of an uncombined element is 0, so is 0. -2 for oxygen, +4 for carbon, -2 oxygen, +1 for potassium, -2 +4. Find out which elements change oxidation state. So nitrogen and carbon. So carbon from 0, it's going to carbon on with the +4 oxidation state, and nitrogen from +5, it's going to +4. Balance the number of electrons lost and gained in partial equation. So carbon, to move from 0 to +4, must lose 4 electrons, and nitrogen to move from +5 to +4 need to gain 1 electron. So as we see, they not balanced, as we have a -4 and +1. So to balance them, we need to multiply the second one by 4. So as you see, I'm multiplying every actually part of that equation. So the 4 actually appear everywhere here, yeah. And we just rewrite the first partial equation once again. And now they balanced. So we just put the right numbers. So that's the nitrogen with the +5 oxidation state. So the 4 is going here. The 4 is going as well here as nitrogen with the oxidation state +4. And balance the remaining elements by inspection methods. So we know that the oxygen and hydrogen we're doing as the last. So first we have potassium. Here we have 4 atoms of potassium on the left side, and on the right side only 2. So to get the 4 on the right side, we need to put the 2 here. So we have a 4 here on the right side and 4 on the left side. And now the last actually element is oxygen. So here we have a 12 atom of oxygen on the left side, and here we have 2 plus 2 is 4, 8 as well 12, and the equation is balanced. In the next video we'll be moving towards more complex equation, but we do as well a little bit introduction to be able actually to do those calculations. Thank you.